from Earth, it's Space Radio. This is Paul Sutter, and coming up, we're talking about Feel, the magnetic attraction of this rogue planet. And if I have time, Ganymede goes nuts. And of course, taking listener questions about all things in the universe, because that's what this show is about. We record every Thursday at 4 p.m. Eastern. Call 888-581-0708 to join the conversation. And in today's Blue Shift, I'll be talking about a warm, welcoming environment. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, chief scientist at COSI. For the next half hour, your agent to the stars got an exciting show for you today on Space Radio, where we talk about all things in the universe. That's how great this show is. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern here in Studio A of WCBE Columbus. Call 888-581-0708, light it up, get those calls in. You can also follow along on our live streams on YouTube and Twitch, joining the other space cadets from around the world tuning in live right now from Texas Hill Country, Seattle, Nagaland, India, Austin, Texas, Boulder, Colorado, Salt Lake City, Kempner, Texas, lots of Texas, competing with 4 people from the UK, including from Guildford and Lancashire. I don't know if that's the name of a city or if you just collapsed on the keyboard. Also, Parrish, Florida, and Lehigh Valley, Pennsylvania. Thank you so much for joining me. You can join them too. Go to spaceradioshow.com for the link. Seriously, folks, a prep 10 minutes to show material tops. So get those questions in. Before I start taking questions, I wanted to share some interesting bits of news I caught recently, and I want to talk about a rogue planet. I want to talk about a planet that is not attached to any solar system in the galaxy. You think that these might be kind of rare, but they just might be the most common kind of planet out there. Estimates range from 100 billion to a trillion of these rogues floating about just the Milky Way galaxy. And just as we see with the exoplanets, with the planets around other stars, we see an incredible variety, a cornucopia, a buffet, a smorgasbord of planetary options around all these other stars. We're also seeing some very strange creatures not orbiting other stars. And I would like to draw your attention to a particular planet that goes by the name of SIMP J01365663 plus 0933473. Okay, so maybe we need to come up with some better naming conventions for these rogue planets, but this is what we got. We'll just call it SIMP for short for now. And check out this planet. This planet is about 12 times more massive than Jupiter, which puts it at the upper range of what is considered a planet. If you're any bigger than that, you get designated as what's called a brown dwarf or a failed star. So it's right on that line between overachieving planet and underachieving star. And something absolutely fascinating about this planet, it has a wickedly strong magnetic field. Estimates put this at somewhere north of 1 million times stronger than the Earth's magnetic field. That would be stronger than any magnetic field in the solar system. That is like magnetic field strength that you would use to diagnose illnesses in your body in an NMR machine. This is crazy strong magnetic fields. How does a planet not attached to any star generate such a strong magnetic field? It must be hot. There must be an extreme amount of heat and convection and moving materials happening inside this planet to generate that field. Now, how in the world do you actually see a magnetic field in a planet that is not even orbiting another star? Well, we don't see the magnetic field itself because magnetic fields are invisible, but we can see aurora. The Earth has a magnetic field. It traps charged particles. They come screaming through our atmosphere. They light up, give us the aurora. Jupiter has strong magnetic fields, traps charged particles, come screaming through its atmosphere, make an aurora. This planet This planet has intensely bright aurora that we can see. We see the aurora, and from that we can estimate the strength of the magnetic field. Now, the aurora on Earth, those charged particles that come screaming through our atmosphere that make the aurora, those charged particles come from the sun. When it comes to Jupiter, those charged particles are spewed out by one of its moons, Io. Now we have a giant planet that is definitely not attached to any star. Where do the charged particles come from to light up its magnetic field? We think, given the two examples we have of making aurora, that this giant planet hosts a moon. We live in a weird and wonderful galaxy. I wouldn't want to live anywhere else. That's the latest and greatest when it comes to space. It's time to have a conversation. And we've got a caller. Hey, Dwayne, thanks for calling Space Radio. Where on Earth are you?
I'm at work in Austin, Texas right now.
All right, Austin, Texas, checking in. So what are you curious about today?
Yeah, I have a coworker at work who's having a problem believing that time is real. It's like the LHC, we've actually measured time deviation going on. Do you think you explained to my friend that time is a real physical entity in the universe?
Great question, Dwayne. This is such a deep question. I love this. Like, is time real? We have to take a step back. We have to ask, one, is anything real? Let's assume that we live in a real physical universe. It's not a figment of our imaginations, and we can study it. We can objectively measure this as basic underpinnings of science. Now, when it comes to time, whenever someone, comes up with something like maybe time doesn't exist, maybe it's just an illusion. Well, we know some things about time. We know some properties of time. And one of the biggest things we know is that time is intimately connected to space. Have you ever heard of this concept called space-time?
Yes, sir.
Yeah. Space-time is exactly what it means. Space and time are united into a single fabric. This is a realization of special relativity, of Einstein's theory of special relativity, not realized by Einstein himself, actually realized by his teacher, Hermann Minkowski, who put forth this webbing, this meshing, this unification of our views of space and time. If time is not real, then space is not real, because we know that time and space are meshed together. We live in a four-dimensional universe. There is 3 dimensions of space and 1 dimension of time. There is lefty-righty, there is uppy-downy, there is forward and backwardy, and there is past to futurey. That is a dimension on equal footing with the 3 spatial dimensions. Now, do we fully understand the properties of time? Absolutely not. Do we understand why time travel into the past appears to be impossible in our universe? No. Do we understand and appreciate time as a real thing? Yes. Time is as real as any spatial dimension. It does have some strange properties that it doesn't share with the spatial dimensions. Spatial dimensions, you can go in any direction you want. I can go left as easily as I can go right. I cannot go into the past as easily as I can go into the future, but they are on equal footing. Does that help answer your question? I'm going to appeal to the special theory of relativity to claim the realness of time. Do you think that will help with your friend, Dwayne?
Yes, sir. Quite a bit.
Do you have while I got you on the line, do you have anything else that's been bugging you? Anything your friend's been tossing at you?
Well, there's been something that's bugging me for a couple of years now. And you hit on it on your radio show yesterday about a finite universe starting off at 0. Is that a reference to a cosmological constant?
Oh yeah, great question, great question. So now we're switching gears a little bit to the large scale structure of the universe. We're asking about the curvature of the universe. What is the geometry of that space-time? If space-time is our universe, how is it shaped? How is it bent? How is it warped on the very largest scales? Now we know from measurements, from direct observation, that we live in a very geometrically flat universe. This means at incredibly large scales, like bigger than a galaxy, way bigger than a galaxy. Parallel lines stay parallel. Angles inside of a triangle add up to 180 degrees. All the geometry that you learned about in high school and then probably forgot applies at very large scales in our universe. It didn't have to be so. The universe could have had any curvature you'd wanted. This space-time fabric, this stage that we all live upon in our universe could have had any shape it wanted at the biggest scales. It ended up being flat. Is that connected to the cosmological constant? Yes and no. The geometry of the universe is the geometry of the universe. What dictates the geometry of the universe is the contents of the universe. These are intimately connected. You change what the universe is made of, you change how the universe is bent at large scales. One of the things the universe could be made of is just empty weight to empty space, a raw weight to empty space. This is a term we call the cosmological constant, aka the vacuum energy. Vacuum energy exists. We have a very difficult time measuring exactly how much vacuum energy there ought to be, but that is what we refer to as the cosmological constant. Thank you so much, Dwayne. 2 awesome questions for the price of 1 caller. I'm Paul Sutter, and this is Space Radio. This show is brought to you by you. Visit patreon.com/pmsutter to learn how you can support this show. I will see you after the break. And it looks like we got another caller. Very cool. We're buzzing. Let me talk to the live streamers for just a little bit. And caller, I know you're there. Ali, I see you're there. I can't hear you, but I know you can hear me. But we will bring you on the show shortly. But I wanted to see. There are so many good you could. Yeah, so Potapom on YouTube, how can we see an exoplanet? In most cases, let me just say, in most cases, we don't see the planet itself. We see the effect the planet has on its system. It either makes its parent star wobble, and we detect the wobble in the star, or it passes in front of the face of that star, and we see a slight dip in the brightness from that star. In some cases, we do have literal pictures of a planet outside our solar system. Those are kind of hard to come by because planets are small and dim. When it comes to rogue planets where there's no star to wobble, there's no star to block, that's very difficult to find. But this is why the rogue planets that we know of are incredibly big. They're incredibly hot. They are glowing in infrared. For this latest detection about this SIMP planet that I just talked about, we saw it actually in the radio because of its strong aurora. So we're doing everything we can to see any kind of planet that's out there. Joyful running on YouTube. Could it theoretically be possible for a universe to have different curvature in different places, like positive in one region, negative in the other? Absolutely, absolutely. So our universe in the vicinity of the Milky Way galaxy is very positively curved because of the presence of all that stuff. You go out into the middle of a cosmic void where there's absolutely nothing, that'll be negatively curved because there's nothing there. But on the absolute largest scales in our universe, once you smooth out all those bumps and wrinkles, all that is tiny, tiny, small stuff. On the very biggest scales, our universe is flat. Launchpad Astronomy, is that planet, that sim planet, a planet or a brown dwarf? For a long time, we thought it was a brown dwarf. We thought it had 20 times the mass of Jupiter. Turns out it's just 10 to 12 times the mass of Jupiter, which puts it right at that line between planet and brown dwarf. And so we're gonna stick it in that brown dwarf, in the planet category. But further measurements might very well put it up into brown dwarf. Thunderduck, I'm actually going to answer your questions in the segment about magnetic fields. Can magnetic fields be harnessed to generate power or used as a method of propulsion? Absolutely. Absolutely. In fact, magnetic fields are used to generate electricity right now. Magnetic fields are how we make alternating current electricity. So if you plug something in, you're actually harnessing the power of magnetic fields. Raj, I might say that again on the line. All right, let's get back to the show. We got this caller waiting patiently. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got another caller ready to go who has been waiting so patiently while I bantered with the Space Cadets in between segments. But remember, you can join the conversation by calling 888-581-0708 or by following the live streams. Go to spaceradioshow.com for the links. Ali, how's it going? Where on earth are you?
Hi, Paul. I'm in Salt Lake City. It's okay in here.
It's okay.
It's a little smoky due to all the wildfires.
I'll take it. It's okay. What are you curious about today?
So my last time I asked a question that is math related to science, and that was a joke. But the serious question is, how close are we to closing the gap between mathematics and physics? And I guess that's the theory of everything. But the question is, if that happens, can we define like a borderline that we say this is where math ends and where physics starts, or we can just?
Yeah, that's a beautiful, beautiful question. I love it about this fundamental relationship between science and especially physics and math. And there are definitely some things you can point to and say, oh yeah, that is totally 100% math. And there are some things you can point to and say, oh yeah, that is totally 100% physics. You slam some iron nuclei against a screen, that's going to be physics. You study group theory, that's going to be mathematics. What if you use group theory to try to understand the behavior of iron nuclei slamming against a charged screen? Aha! Is it math or is it physics or is it both? So physics is a branch of science. And as a branch of science, there are certain obligations and expectations that are incumbent upon it. For example, every statement we make must be, at least in principle, falsifiable. You must be able to come up with some experiment that could demonstrate that you are wrong. Also, you must tie to existing physical theories. So you can't just go out there crazy. You must be able to make predictions. You must connect to all the other things we know about the universe. And you must make it real, I suppose. You must make it connect to the physical universe. Mathematics, you're under no such obligation. You're just studying very complex logical structures and using axioms to see how far you can go to reach conclusions about these logical structures. Physicists use mathematics as a toolkit, as a way of understanding nature, as a way of modeling nature, as a way of making predictions. There are some incredibly theoretical areas of physics. Areas of physics with no known observational tests, with no known predictions. And this is the realm where it starts to get really fuzzy and bleed out into just pure mathematics. And there are some physicists, I'm looking at you, string theory and loop quantum gravity, where it's basically mathematics, which is okay. At some point, if you want to keep sitting in the physics department, you probably have to come up with some sort of observation or testable prediction. Is a proposed theory of everything. Like a lot of physical theories start off as pure math of just, hey, let's just take this idea and run with it. General relativity was a lot of pure math for a while, for years actually. But at the end of the day, you must make verifiable predictions so that we can test your idea. That is the boundary line between physics and math, is where predictions and testing can be made, where the rubber meets the road, where the raw ideas as represented by mathematics meet the actual observable universe. Thank you so much, Ali. That was a beautiful question. Now, there were a few questions I want to catch up on from the Space Cadets, especially Raj Luthra on YouTube and also Thunderduck on YouTube, asking more about magnetic fields. Like, I mentioned this giant rogue planet has these massive, beautiful magnetic fields. So what's going on with magnetic fields? Do they have mass? No, a magnetic field is just a field of magnetism. It doesn't have any intrinsic mass on its own. Do they travel at the speed of light? Well, here's an interesting thing about magnetic fields. If you just take a magnetic field and you start wiggling it around, you start changing it, you will create an electric field. And if you take an electric field and start wiggling around and start changing it, you'll make a magnetic field. They're kind of connected like that. Changing an electric field makes a magnetic field. Changing a magnetic field makes an electric field. So what happens if you take an electric field and start wiggling it, and you keep wiggling it? Well, you'll make a magnetic field, but that magnetic field itself will be changing, which will be making an electric field, which will be making a magnetic field, which will be making an electric field. They'll keep waving back and forth. In fact, they'll start propagating. They'll start moving around. They'll start zipping from place to place, these self-reinforcing waves of electricity and magnetism, an electromagnetic wave, aka light, radiation. The light slamming into your eyeballs right now is really waves of electricity and magnetism reinforcing each other. We got that realization from James Clerk Maxwell in the mid-1800s. He developed a set of mathematical equations, there's our connection to math, that unified our pictures of electricity and magnetism and ended up inventing light. Back then, before then, no one could see anything until Maxwell said, let there be light. And then the question from Raj Luthra about Luther is can a magnetic field be harnessed to generate power used as a method of propulsion? And absolutely, a magnetic field is a field of force. It can push things around. It can be pushed. In fact, electrical generation, the most common form of electrical generation, depends on magnetic fields. We depend on changing electric fields to become changing magnetic fields to draw electrical currents and push them around to generate them, to shove them down wires and to power everything from your light bulbs to your smartphones. Your electricity that you are using right now owes its very generation to the power of magnetic fields. Magnetic fields, the unsung heroes of the universe. I have a soft spot for magnetic fields. I feel like they don't get a lot of airplay. I feel like they don't get a lot of attention. Sure, they're not a dominant force in the universe or the solar system, but they mean a lot to me. Okay? Sometimes I like to give a shout out to the underdogs. Good old magnetic fields. In fact, next month I have an episode on Ask a Spaceman, my podcast, devoted to the humble magnetic field. So stay tuned for that. You can go to pmsutter.com or askaspaceman.com for links to my podcast where I'm going to dig in nice and deep into the wonderful world of magnetic fields. Thank you so much to all the wonderful call-ins today and the Space Cadet questions. We're almost out of time today on Space Radio. Before we go, it's time for the Blue Shift. I love all the magnetic field questions. Those are absolutely fundamental questions. about this force that, like I said, it doesn't get a lot of airplay, doesn't get a lot of airtime, but it really deserves it because it really is so important. It's just almost every astrophysical system you look at, magnetic fields play some role. It's almost always not the dominant role, but it's something. It's something. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get just a little bit closer to you. And I want to tell you about an event that, if you're listening to this on the radio or as a podcast, the event is already over. I'm sorry about that. I would love to give you a little bit more warning, but it just spun up, just got organized yesterday, which is Wednesday for me. And the event will be tomorrow, which is Friday, August 10th for me. If you go to facebook.com/science channel, that's facebook.com/science channel. I'm doing a live Q&A at 1:30 in the afternoon Eastern, talking all about the launch of NASA's Parker Solar Probe, which hopefully next week on the radio I'll get to talk about its launch and the mission and all that. But this is a Q&A, I'm sure, like any live Q&A, as you can see, is going to go in all sorts of weird and wonderful directions. So I will take any space-related question. That is facebook.com/science channel. And as we were creating this event, I was talking with the social media team at Discovery Networks and Science Channel to create this. The topic came up, the discussion came up of like, how do you get people to ask questions? Just how do you make an environment where people feel comfortable asking a question? Like, the callers that call in on this show are incredibly brave people. They're putting themselves out there to call into a radio show that will be recorded and broadcast. And people don't like to look dumb. People don't like to look ignorant. People don't like to look like they're not knowledgeable or erudite or experts. I sincerely hope that the environment that I create in this show, Space Radio, and all the shows that I do, is an environment where you are welcome to ask even the most simple, basic questions about the universe. Because you know what? You might think you have a dumb question because it's so simple or so basic, but simple questions and basic questions are exactly where physics start. The most important, the most powerful questions that we ask in science are the simplest, are the most basic, are the first questions you might ask. The first question you might ask will be the question that guides generations of scientists through decades of research. So any question you have, if you want to ask, I will never judge you for your question. I will never criticize you. I had a comment I saw on Twitter the other day after last week's show where it said, oh, I'd love to listen to you, but the questions you get, sometimes you get dumb questions. I shot that down hard. I do not get dumb questions on this show. I absolutely refuse to acknowledge that. So if you've got a question, if you're curious about the way the universe works, talk to me. Talk to me, and we're going to have a conversation, human being to human being, person to person. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of Space Radio. Once again, I'm Paul Sutter. This show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. This show is also brought to you by you. Go to patreon.com/pmsutter to learn how you can contribute. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, Dan Michalko for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday, 4 p.m. Eastern. Call 888-581-0708. You can also call that number anytime and leave a voicemail. And you can also catch the YouTube and Twitch live streams. Go to spaceradioshow.com for the links. And of course, thanks again, Earthlings, for listening. See you next week. And remember, science is for sharing and transmission. I didn't know I'd get fired up in that blue shift. I felt the spirit move me. All you space cats, all you callers, I love you. Like, you have no idea. You are making this show possible. It is your questions that make the show. No, I don't. I'm not able to answer every single question on the show, and I'm sorry. Scott Bragney, you're asking about updates on making it 1 hour. We are still working on it. We really are. We were originally hoping for September start. We don't know if we can hit that. We're waiting on, we're hoping if Patreon were to jump up by like $200 or $300 a month, we would be able to do it right now. Absent that, we are looking for underwriters, for sponsors. We're chasing every possible lead we can. And so hopefully now our new target is hopefully October for the start of a 1 hour show, like at our 1 year anniversary. We're working on it. But hey, if you got $300 a month to spare, put that sucker on Patreon and we'll make that 1 hour show happen right now. I mean, no pressure. No pressure to you. I'm just saying that's if we hit that goal, if we hit 1,000 a month, we can produce a 1 hour show and pay all our bills. And yeah, sorry if you don't do social media, I'm very sorry. On Facebook and Twitter, I'm sure the video will be archived. And then I will post it, like I'll do an embedded link thing on my website so you can watch the video from the safety and comfort of not being inside Facebook. So thank you, all space guests. Sorry I didn't get to all the questions, but that's life, man. That's life. Mysteries still need to remain, and we still need to do a show next week. So I will see you next week. Thank you, all the space guests, and thank you again, Nancy.